Hi, my name is Fereidoon and welcome to my electrical training channel. If you found this video informative, you can help me rank higher on YouTube by hitting the subscribe and like buttons. Please comment below and let me know if you have any suggestions for our future videos. Right, welcome back to another exciting lesson on electrical and electronic principles. In this session, we're talking about resistors in series and parallel connection. By the end of this session, the students will be able to apply Ohm's law and Kirchhoff's law accordingly and be able to transpose the formula for any required item of the formula. Be able to calculate the total resistance and the voltage drop, the components in single source purely resistive DC series circuits using Kirchhoff's voltage law, and be able to calculate the total resistance and the current in each leg of, again, single source purely resistive DC parallel circuits using Kirchhoff's current law. Be able to use the current division formula to find the current in each leg of a two resistor parallel circuit using the total current value and the value of each resistor. Be able to apply all the above rules in combination of series and parallel circuits, and finally be able to answer the questions. Teaching Ohm's law. But briefly going through, in 1827 George Simon Ohm discovered that there was a definite relationship between voltage, current and resistance in an electrical circuit. Ohm's law defines this relationship can be stated in three ways. 1. Resistance R is the opposition to current I, the flow of electrons. Resistance of a circuit is voltage divided by the circuit current. A mathematical representation of this concept is R equals E over I, or voltage divided by I, current. The second way of explaining Ohm's law is current I is the flow of electrons in a closed circuit. Current is equal to the applied voltage divided by the circuit resistance. A mathematical representation of this concept is I equals E over R, or voltage over resistance, R. And the third way, or third method of showing that relationship is voltage, or electromotive force, or EMF, another term for it, is the electrical pressure needed to make electrons flow. Applied voltage equals circuit current times the circuit resistance. And the representation of this concept is E, or voltage, equals I times R, or IR. Right. Therefore, with respect to Ohm's law, the relationship between current, voltage and resistance in a circuit is this formula. I equals E over R. The current in an electrical circuit is directly proportional and inversely proportional to the resistance. Now you should be able to do the exercise 1. Coming back to Kirchhoff's law now. Kirchhoff stated two laws. The first one is the current law and the second one is the voltage law. Kirchhoff's current law, or current rule, states that the currents flowing towards a node or a junction are equal to the currents flowing away from that node or junction. No vectors required for DC. We're at the moment dealing with DC, but in any junction, in any network, any circuit, if you have a junction or a node like this, the sum of all the currents going towards this junction, like I1 and I2 in this example, equals the sum of all the currents going away from that junction, I3 and I4. You can state that formula. Simple as that. So if I1 is 2 amps, I2 is 5 amps, and I3 is 4 amps, then you can find I4 So I4 must be how much? So I2 and I1 and I2 are 7 amps altogether, and I3, which is leaving that point, that junction, is 4 amps. So I4 must be how much? Yes, that's right, 3 amps. Kirchhoff's voltage law states that the sum of the voltage drops around a series circuit, a closed loop, is equal to the source of supply. So if this is your source of supply and this is a series circuit, the sum of all the voltage drops across the circuit, like V1, V2 and V3, should be equal to V supply, or Vs. In this case, we've substituted, instead of V1, we've written down here I times R1, I times R2, I times R3, which is the equivalent of voltage drops across each resistor using Ohm's law. So that's your formula for Kirchhoff's voltage law. That applies in series circuits. So if R1 is 50 ohms and R2 is 100 ohms and R3 is 25 ohms and voltage equals 87.5 volts, or voltage of the supply, some will state Vs instead of this because they want to indicate this is the voltage of the supply or battery or it's a source of supply. Then I, voltage divided by R total resistance, this is Ohm's law. We can find the current first. The first thing you do is you have the voltage, you find the total resistance, you just add them all together because they are in series. The total resistance is sum of all these three, 50 ohm, 100 ohm and 25 ohms. That's 175 ohms. So that comes here. And the voltage is 87.5 volts. It's given. You divide that voltage by resistor, you find the current, which is 0.5 amps. That's going through the whole circuit. And current in series, we've stated this before, and we reiterate here, current in series is constant. That means if you have an ammeter at this point, or this point, or here, all your ammeters should be showing the same readings. It should give you the same readings, because it's series and the same current that starts from here, it goes all the way through all the resistors and come back to the source of supply. There is no junctions. There is no division. Current doesn't split in this circuit as it does in the parallel circuits or other networks or combinations of series and parallel. So you found the current now. First thing you did, you found the total resistance, divided the voltage by total resistance, you found the current. Now current times each resistor will give you that voltage drop across that resistor. So current times R1 will give you V1, this voltage across here. Current times R2 will give you this voltage, and current times R3 will give you that voltage. So you put the values there. Current is constant, as you see, 0.5, 0.5, 0.5 for all three of the voltage drops. Times each one by the resistance. Times 50, I'll give you 25 volts for V1. You could name this V1 instead of IR1. And V2 is 0.5 times 100, that's 50 volts. 0.5 times 25, that's V3, and that's 12.5 volts. Now if you add them all together, you see 25 plus 50 plus 12.5 adds up to 87.5 volts. If you haven't rounded the values up, it should give you exact same as the supply source. And the Kirchhoff second law rule, the Kirchhoff's voltage rule applies. Now your teacher will give you the second exercise, and you should be able to answer all those questions. Resistors in parallel now. If the resistors are connected in this configuration, that means both ends of the resistors are joined together. So the beginning of the resistor, both legs are connected together, both ends. And there is a junction here, and there is a junction there. So as you see, current that comes from the supply, when it gets to this point, it splits. Part of that current goes through R1, and part of that current goes through R2. All depends. The amount of I1 and I2 depends on the size of the resistor 1 and resistor 2. The bigger the resistor, the less the current goes through this. That's according to Ohm's law again. Ohm's law always applies. So if R2 is small or smaller than R1, I2 will be bigger than I1. If R1 is smaller than R2, I1 will be bigger than I2. So that's the Ohm's law again. And because we have a parallel circuit here, we can write for this junction or this node. Because you have a junction here and current splits here, we can write Kirchhoff's current rule or current law's equation. I equals I1 plus I2. And that way we can solve some of the questions and some of the problems. Now, since the voltage across both resistors is the same, if you go back to the same screen, I can show you the voltage. If this is the voltage of supply, this is the same voltage that's across R1 as it is across R2. The voltage doesn't change. The voltage is constant in parallel. So in series, current was constant. Now in parallel connection, voltage is constant. Imagine a hallway with lots of lights, with 10 lights, and all of them connected to the source of supply. Let's say it's 240 volts supply, and all of them are connected to the same supply. If you take a voltmeter and measure across each lamp or each light, you will have 240 volts, unless the length of the cables are too long and you've dropped some of the voltage along the line. But if they're all in one room or in a small hallway, then you should be they should all show you the same voltage, almost the same voltage. I say almost because the wires themselves have some resistance, so you might get a little bit variations of voltage between the lights. But generally, if they're parallel and the resistance of the wires themselves, the conductors themselves, are negligible, then the voltage is constant. But what splits here is current. Current splits, voltage is constant. Whereas in series, current was constant and voltage was divided between the resistors. So because of that, we can write in parallel circuit, we can write the Kirchhoff's current law's equation, I equals I1 plus I2. Sorry about this, 2 missing. And then replace them using Ohm's law. Substitute I with voltage divided by R, that is, as in RT or total resistance, equals V over R1 plus V over R2. So we substitute each one of these current using Ohm's law. We factorize V from the equation from both sides. So you have V factorized and you're left with this. 1 over R equals 1 over R1 plus 1 over R2. Now if you do the common denomination, R1 times R2 is the common denomination, and you have on top R2 plus R1, which is because you have common denomination R1 plus R2 divided by R1 will give you R2, that's the R2, and R1 times R2 divided by R2 will give you R1, and that's R1 on top. R1 plus R2 or R2 plus R1 divided by R1 times R2. And now if you flip this to find R, because we're looking for R total resistance in parallel circuits, if you flip this, 1 over R will turn to R, and then this will turn to R times 1, R1 times R2 over R1 plus R2. We call this formula, or this equation, product over sum. So this resistance in parallel circuits can be found by this equation of product over sum. Now, one thing I have to say here is that this formula only applies in parallel circuits if and only if you have 2 resistors in parallel, not more than 2. If you have more than 2 resistors, you still have to stick to this formula. This is your formula: 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. If you have more, plus 1 over R4, and all the way to the end of your to the last resistance. And then once you calculated the whole overall sum of reciprocal values, then you have to inverse the value to find total resistance. And some students just leave it as that, and what they found is 1 over R. It's not R total. You need to inverse the final value. You'll see that in exercises. So therefore, for a circuit with a considerable number of parallel resistors, 1 over R equals 1 over R1 plus 1 over R2 plus 1 over Rn, n being the number of resistors in the circuit. And if you have 2 resistors in parallel, you can just use product over sum, which is the simpler version of this. It's the same thing, it's just been simplified. Now you should be able to answer more questions on parallel circuits, which will be provided probably by your teacher. Current division between parallel resistors. Now, if you have 2 resistors in parallel, to simplify things, you can still find the current by using the Ohms Law and Kirchhoff's law, combination of them. And that's what we're doing here. But we're trying to find the formula. So it always applies if you have 2 resistors in parallel and you want to find the current of I1 or I2 when you have total current and these 2 resistors. And you don't want to go around, find the value of the total resistance and then times the current by total resistance, find the voltage drop, and then divide the voltage drop by each resistor to find each current. You just want straight go to I1 and find I1. So we're trying to formulate that. Like I said, this only applies if you have 2 resistors in parallel in this configuration. Right. A circuit with 2 resistors in parallel, and you want to find the current in each branch without having to go to find the voltage across the resistors. Now, there's 2 methods to do that, to find the current in each branch. If you have the current and 2 resistors of each branch. One was the ordinary method, which is what we used to find the current in each leg or branch of the circuit when we were solving combinational circuits with resistors and resistors in series and parallel combined together. What we did was basically finding the total resistance of that part of the circuit. In this case would be, we would name this RT1, the equivalent of these 2 together, which would be 1 over R1 plus 1 over R2. Once you found the total resistance or equivalent of the resistance of these 2 branches, you times that RT1 by this current to find the voltage across this branch between this point and that point. That would give you V1 RT1 times I. That's the voltage drop between these 2 resistors, between these 2 points. That's as if you have a voltmeter and you put one probe here, one probe there, that will give you this voltage drop. We name it V1. Then you would go and find I1 using Ohm's law, V1 over R1, and I2 would be the same voltage because it's parallel. They are connected together in parallel format connection. So voltage across R2 would be equal to voltage across R1. So V1 over R2 would give you I2. But that was the way we did this, and we can still use that. It can still use at any time, at any point. But sometimes it's good to know that there is a different method, and if you know that, you might have a shortcut to the result. So if you want to find I1, I'm going to give you an I2. If you want to find I1 or I2, or both of them, I'm going to give you a formula that you can use it. We call these type of circuits current dividers. You can use these type of these formula or equations for this type of circuits, the current dividers, to find I1 and I2. I'll give you the final formula that you can use, and then I'll prove it to you how it came about, these two equations, how they came about. But you don't necessarily need to know how to prove it, but you need to know how to use them, and therefore I'll just give you the formula, and you see I1, this current through this resistor, this branch, equals I, the current, the total current, I, times this resistor of this branch times R2 over the two resistors added together, R1 plus R2, and we put them in parentheses so they are, you don't make mistakes when you're doing when you're putting the values in your calculator. And you can guess what the I2 would look like. The formula for I2 would look like. I2 would be I times, so if you want, that was for I1, I times R2 divided by these two added together, that was that. Now if you want I2, that's this again times this other branch resistor over the same thing, I times R1 over R1 plus R2. So that is your formula for I1 and I2. It's simple enough, and you can use this at any of these type of circuits if you have current dividers. Just to remind you, current dividers, if you have resistors like this in parallel, current divides or current splits. In series, if you had resistors in series like this, we said current was constant, so you had a voltage supply and current was constant throughout the circuit, but what divided was voltage. You would have V1 and V2, and the sum of those two would be equal to the sum of the voltage of the supply. In parallel, voltage is constant, but current splits or divides, and the sum of these two currents would be equal to the current of the supply, or the current that comes in is equal to the sum of all the currents going away. Now, these are the formula for current dividers. You can find basically I1, I2 using I and R1, R2 without having to find voltage drop. But I'm going to prove this to you, where they come from, for some zealous learners. They want to know where those equations come from, so I'll prove it to you. If I write the voltage across these 2 points equals I1 times R1, and because it's parallel, you can say it's also equal to I2 times R2. That is my equation number 1. And also, at the same time, I could write the Kirchhoff's current rule, which says I equals the current that comes into the point equals to the sum of the current that are going away from it, I1 plus I2. And that is my equation number 2. From these two, I can prove those two equations I just gave you. So, if I rearrange this one for I1, I'll get I minus I2. Now, instead of I1 in the equation number 1, if I replace I1 for this, substitute I1 with that, then you get I minus I2 times R1 on this part of the equation equals to I2 times R2. Now, multiply R1 through this bracket, I R1 minus I2 R1 equals I2 times R2. Take this part of the equation to the other side of the equation. This part, because we want to separate I from I2, I times R1 equals, now because it's negative, I2 times R1 is negative. When it goes to the other side, it becomes positive. So you have I2 R1 plus I2 R2, which is that. Now you have this. I2 is in, you have common I2 in both of them, so you can factorize I times R1 equals I2 times R1 plus R2. And you're looking for I2. Just briefly go through the transposition part of it, because some people are struggling with transposition. If you're looking for I2, then you need to eliminate whatever is multiplied by that, which we call it coefficient. So the coefficient needs to be eliminated. To do that, you need to divide it by itself. So you have R1 plus R2 at the bottom here, so they would basically cancel each other. But whatever you do on one side of the equation, you have to do on the other side, so you keep the equilibrium. You keep the equation balanced. So R1 plus R2 on this side. Now what you left, these two cancel each other, so I2 equals I times R1 over R1 plus R2. There you go. That's exactly what I told you to begin with. That's the formula I gave you for I2. Now, you can do the same thing, follow the same procedure, same pattern, and rewrite I2 from this equation. Let me write it in a different color. I2 would be I minus I1, and replace I2 with this in here, and rewrite this equation like this, but just use this part as it is. I1 times R1 equals I minus I1 times R2, and follow the procedure. See if you can find, so this is your task, see if you can prove I1 equals I times R2 over R1 plus R2. And that is your formula. So these are your formulas for I1 and I2 in current dividers. Right. If the resistors are 7 ohm and 3 ohms respectively, and I equals 10 amps, then I1 is, this is your formula, we just proved this, and I2 is this, and then you put the values there, bam, you've got the answers. Now at this point you should be able to answer exercise 4 questions, which will be presented to you by your lecturer. Combination of series and parallel circuits. Now if you have a circuit like this, you have to break it down into step-by-step circuits. You have to break it down into little steps. So what you do, you start from the part of the circuit that is easier for you to do and is possible. The first thing you do, you need to find the total resistance. If you, for instance, in this question, you're asked to find the current in each branch, current through each branch of the circuit, and voltage across each part of the circuit or each resistor, as is indicated with voltmeters and ammeters, then what you do, you find the total resistance first, and to do that you have to replace these branches of parallel branches. Like you have a parallel branch here with two resistors, and you have two branches of parallel resistors here. You put, instead of these two, the equivalent of these two, which will be the total value of the total equivalent value of these two will be RT. You name it yourself. If they're not already named resistors, you name them. You start from one corner and say R1, R2, R3, R4, R5, and you name, let's say you name the equivalent of R1 and R2 RT1, and say RT1 is 1 over 100 plus 1 over 100. So the reciprocal value of 1 over 100 plus 1 over 100. And that will give you 50 ohms for that part. So 50 ohms will be the equivalent of these two. So you have one resistor here instead of two resistors in parallel. You have one resistor with a value of 50 ohms in series with 330 ohms. So now you can add these two together and put another one resistor there, and that will be 330 plus 50, that's 380 ohms, and that is in series with these two in parallel. So again, you find another RT2, you name that RT2, the equivalent of these 200 and 300s, 200 and 300 ohms, and whatever it is, the value 100 something, then that will be added in series with 380 ohms resistor. So all your total would be let's say 470 ohms or whatever the value is. And then once you have that, voltage divided by the total resistance will give you the total current. And from the current division laws that we just proved, you can find those current that split here, I1 and I2, and when they get here, it's the same current as I total, because it's Kirchhoff's law. Current coming towards the point is the same as the current going away, which is the same. So it's the same current that was leaving here, coming towards this point. It's the same current that's leaving here. It's the same current going through this resistor and then splits here, and you can find that using those current division laws. Or another way to find these two branches, because you're already asked to find the voltage of each resistor, then once you have the current, total current times the equivalent of these two resistors will give you this voltage, times the same current times this resistor, because it's the same total current that goes through this resistor, times this resistor will give you this voltage, V3, and the same total current times this equivalent of these two, not the 200, not the 300, the equivalent of those two will give you V4, or voltage drop 4. And then once you have the voltage drops across the circuit, divide each voltage drop by that resistor which is across it, and you find the current through that branch of the circuit. So if you have V3 divided by R3, you find I3. Now these are ammeters and voltmeters. Some learners have noticed they write A3 equals such a thing value. It's not A3, that's just an ammeter, that's an instrument. This is an instrument. It's I3. Or you could name this one, in this case, it's I really. You have I1, I2. This is I, still I, as I total, that comes here, comes back to I again. You could say I3 equals I, or I total. and then I4 and I5. V1 is equal to the source of supply. So the voltage that you have across the battery, that is what you're measuring here. Right? Last exercise for this part, and I'll see you next time with another exciting lesson on electrical and electronic principles. Goodbye for now.